Welcome to everybody for this meeting dedicated to robotic spectroscopy. We will have some many attendees this night, and this meeting is recorded, and it will be available tomorrow on the Chevalley YouTube channel in replay. So now I give the leave to François.
So hello everybody. This is I'm talking, and at the same time I will try to share my presentation, and it will take 1 second. Okay, so welcome to everybody. This is really a pleasure to have this new meeting. I'm very happy to see that there are so many attendees and so many participants. When we started thinking about this meeting, I did really think that we would have 15 or 20 person online, because this is a very, very technical subject. And in fact, it looks to be interesting for a lot of people. So this is really a pleasure. And it was also a great pleasure when we started organizing this meeting, when we asked a lot of people to participate and to present and to share their own experience in automatic spectroscopy. Everybody agreed, and then we have a lot of speakers tonight, and very experienced people. And really the idea is to share all the experiences, and this is a great feeling to have this sharing. I will be very short, because I want to give the microphone to the people who have a real experience to do spectroscopy on the sky. This is not, I mean, automatically on the sky. So this is not my case, even if I have something to share. And then I will just give some points to clarify the ideas, and then we will pass to the real speakers of this meeting. This astronomical, the question of putting the star in the slit is, again, it is very, very highly technical subject, and again, I'm surprised that we have so many attendees. And in fact, we have automatic observations for some time now in astronomy, but and we have a lot of experience all over the world. But in spectroscopy, the subject is still new, and we have a few persons, most of them are in this meeting, a few persons that already did some automation of their setup. But I think that the reason for this, the fact that it's only the beginning in spectroscopy, is that we have some specificities in automatic spectroscopy. The main one probably is that we have no universal solution like in imaging. In imaging, everybody doing imaging has the same kind of requirements. They need to take picture of the target, flat images, dark images, bias images, and that's it. And whatever is the instrument, the principle is always the same. In spectroscopy, this is very dependent on the instrument and on the scientific program. So if you are doing low resolution or high resolution E-shell spectroscopy, it's different. And also, depending on the scientific program, what you are looking for, you may have to adapt your observing program. And there is also something important to understand in this spectroscopy, automatic spectroscopy, is that you have to select your instrument to choose a camera, a telescope, a spectro, and so on. But once it is done, during the night, you have one mission, which is to put as much photons as possible in the slit. A difference between a good and a bad observation is the number of photons that you have been able to put in the slit, in the spectroscope. with the same equipment. And to do that, you have mainly to think about three parameters. The first one is the focusing, so focusing the slit in the guiding image and focusing the star. The second one is to make sure that the guiding parameters are correct to keep the star at the same place during all the observations. And the most important, probably, and the reason for the meeting tonight is to put the star inside the slit and exactly inside the slit, not somewhere close to the slit, but really inside the slit. And this is why we are talking about this subject. This is because it is really, we are at the center of the technical requirements to do automatic robotic spectroscopy. I do have one ambition. I'm sure that we will do it, is to develop a network of spectral observatories, fully robotized, so totally autonomous, based on open source tools and developed in collaboration with the astronomical communities. And when I mean communities, I mean the amateur community and the professional community. And really, we have something wonderful to do in the coming years around this subject. And so we'll talk about that more and more in coming months, I hope. And well, I have few reasons in this slide, but I will not spend too much time now, but this is really the idea. By the way, I'm working at home. I do have my own installation with the RC8 telescope in a shelter, and the plan is to make it robotic, of course. And I'm also playing with this small instrument for some time now, which is which is a small instrument, very pedagogic, very it's a toy in fact, and I can do very easy demonstration of spectroscopy. And by the way, I do have replaced recently the AZR, but by the StellarMate box, and the StellarMate box has the advantage. It is very similar to the AZR, but it is a fully open source system, and then I can control any kind of camera, including an ATIC camera, for instance. Well, this is just a detail. Now, why is it possible to do this automatic spectroscopy today in 2025? This is thanks to several key tools. So we had the GOTO mount for some time now. We had the digital imaging also for some time. And we have some affordable commercial spectroscopes, well, thanks to Chevalley, but even if I know that a few other ones did exist before Chevalley, but well, I do consider that this is with Chevalley that we had the quantity of spectroscopes in the field. And we had also, this is important, and we'll talk about that tonight, the auto-guiding software. I don't know exactly when it did start, but it was probably around 2009. And maybe I'm wrong there, but this is the information I've found quickly. And we also now have the plate solving, which is something that is totally transforming, changing the astronomy, because we can make a lot of observations, automatic observation, and this opened the door to wonderful instruments like the automatic telescopes that we have today. And of course, we have very powerful and affordable computers, and we have fantastic pieces of software. And thanks to that, we can do wonderful things. And I just want quickly to clarify a few ideas. Especially, I did spend some time on thinking about how accurate, what is the accuracy I need when I put the star in the slit. And I've made some measurements that I will discuss in a few seconds. And the other point is that I also made some measurements on pointing accuracy of these small instruments. And of course, it should be done the same with any instruments before defining the right strategy to do the pointing. Okay, so I did a few days ago something that I wanted to do for a long time. And this is to write a Python script to put the star at different position through the slit. And then, so this is Altair, if I'm right, I'm almost sure. And the idea here is to put the star above the slit and then close to the slit and then inside the slit, right in the middle of the slit, and then below the slit, and so on, so on. I did select 11 positions around the slit, and I used PhD. So when I said that the script gives the position, in fact I give the target position to PhD. So the Y position here, and that at 11 different positions. And in fact, the important point also is that I use the multi-star pointing system of PhD2, and the advantage is that it did not guide on the star itself, but in multiple stars around this image. So it gives a very high accuracy. And when it was in one given position, one of the 11 positions, then I did measure the flux, the spectrum, in fact, in the science image. It is an LP600. And the idea is to measure the total power of the total light level in the image in 7 different images. For each position of the slit, I took 7 images. And then I measure this, the value, the average between the 7 images and the RMS. And this gives this graph, which is very important for me and which is very pleasant. And I could spend 1 hour on this graph because it gives a lot of information. One of them, for instance, is that when we are in the middle of the slit, we have a very stable measurement. And where we are close to the edge of the slit on one side or the other, we see that the RMS is much higher. And this is normal because it will depend of the turbulence, it will depend on the auto guiding and so on. And another interesting thing here is that I do have a plateau, and I do have a plateau because I'm using a small telescope, the 72ED, which has, I think, 420 millimeters focal length. And in fact, the image of the star at the focal plane is smaller than the slit. The slit is the standard slit from the LP600, which is 23 microns. And then I do have some kind of oversampling. This plateau means that I can move the image is smaller than the slit. And then I should use a smaller slit to get a better resolution. But what is important here is that even if I see the pixel position here, so the center of the slit is close to 650. So the pixel number 650 in Y position. And I see that if I move by 2 pixels, I may lose something like 30 or 40% of the light. This is to say that really we must be putting the slit precisely into the slit. By the way, in the image, the slit width is something like 8 pixels. So I see that even with some oversampling, if I move by 2 pixels, I will lose 30 to 40%. Okay, so really for me, the message is we must put the slit not only in the slit, but precisely into the slit. And I do consider that we must be able to control its position up to something like 1/10 of the slit width. By the way, here we are talking about something like, if I'm right, 8 arc seconds on the sky. Well, I said that by memory. I did measure something else. It was at the OHP. I did something very simple. Again, this is another Python script. The idea was to point at a star, Deneb in this case, and then move away by 10 degrees in a random direction. Okay, and then point again to Deneb, and away by 10 degrees and back to Deneb, away by 10 degrees in a random direction each time, and back to Deneb. And I did that, I think, 19 times. So it was again something totally automatic. In this case, I didn't have any auto guiding. I did have a reasonable pointing polar alignment of my mount, and so no activation of the auto guiding, and I did measure the position, the exact the accuracy of the position by blade solving, by using astrometry.net, and I see that well, if I let the system working alone, I have a precision of something like plus or minus 30 arc seconds. And I said before that I should need something like between 5 and 8. So this is really for me the demonstration that the pointing accuracy of my mount is not enough. And by the way, it is a very good mount. So this is a small AM3 mount from the ZWO, a very modest mount, but it works very, very well. And in fact, I did use precisely all these measures to see, to try to find exactly what happened. And it is very interesting because, for instance, I did measure clearly the periodic error of the mount on one axis. And in deck here, I did measure, I'm able, in fact, to detect very precisely the polar alignment error. And by the way, I did write a paper, so you can find the address here, or I can send it to you if you are interested. It is not published yet. I still have to add some things in this paper, but I did a summary of all my measurements and the conclusion I can make, and especially at the end, I can define a pointing strategy to make sure that it will work in any case. But I still have to validate this in the field, and for that reason, I will not go further tonight. What I've understood so far with all these tests is that first we have a very heterogeneous equipment. Then we have, I'm sure that no go-to mount can place the star by itself in the slit with the sufficient accuracy. So the go-to is not enough, and we have to add something, even if the go-to is very precise when you have a pointing model and so on and so on. But I've never seen a go-to system able to put the star exactly in the middle of the slit. The star, I do consider that the star must be positioned with an accuracy of 1/10 of the slit width. I do consider that the best way to measure the precision is to use the astrometry, so the plate solving in the image. So it is very precise, and the precision of the plate solving is enough to reach the 1/10 of the slit width. The other point is that the only relative movement I can have from my mount is to use the auto-guiding process. When I change the target position in PhD2 auto-guiding system, the mount can move with a very, very small movement. But if I ask the mount to go to a specific position, the precision will not be enough. Well, this is really because of the capability of the encoders in the mount. And what I've understood also is that there is a critical point, which is if we, so I'm able with my system, because this is a short focal length, I am able to do the plate solving at any position in the sky in the guiding image. So again, this is because I do have a small instrument. By the way, this is another point. Using a small instrument is always easier than a big instrument. And in this case, so the plate solving, I can do plate solving in the guiding image. But if you can't in your system, and in a lot of cases it's not possible, then the problem is totally different, and the way to solve it is different. We'll have a lot of people talking about that in a few minutes. Keep in mind that the slit or the hole can move in the guiding image because of the rigidity of the instrument. So you have to put that under control also, and make sure that you know exactly why is the position of the hole or the slit. And by the way, we have in Python very powerful libraries, for instance, to do the conversions between the radix and the unit and the pixels unit. And this is something very fun when you have the tools. in your toolbox. The idea when I'm thinking about all this process and talking about pointing strategy, I'm really thinking about small instruments, middle instruments like mine at home, or big instruments. And this is just a picture I like. I went to Abastumani in Georgia 1.5 years ago to install a hook there, and it was a brand new ASA telescope of 1.5 meters. And the idea is really, even for such a telescope, the question is the same. So how can I point exactly at the star? Now, I will stop speaking. I've been already too long. Anyway, here are the speakers that will start now. So we have Sean Curry from the US. We have Thierry Lemoult from close to Paris, from France. We have Patrick Fricker, who is in Swiss and who controls his instruments in Spain. We have Patrick Chevalley, who is the author of CCDCL software, which is more and more used by amateur spectroscopists. And we will have also Stéphane Charbonnel and Olivier Garde. Well, tonight it will be Olivier Garde who will explain the way they work at two-spot installation. And we'll finish with Peter Velez, who is sorry, in English is not necessary. Peter is in Australia, and so it's very early in the morning for Peter. Thank you for being here. And the idea is that each of us talks for 10-15 minutes. Again, I've been too long. And we can take few questions after each talk. And the idea is that if you have questions, put them in the chat, and Olivier and myself will have a look, and maybe we will ask the question, or we can also interrupt the speakers if it makes sense. And we can also keep the questions for the end of the session. Okay? So I stop here. Thank you very much. And now I give the microphone to Sean Curry.
Thank you, François. I'll spend a few minutes talking about my automated data acquisition system that I call GetSpec. But first of all, I'd like to thank François and Olivier for organizing and presenting this seminar. This is a really interesting topic, and I'm glad to talk about what I've been doing, but I'm also really interested to hear what everybody else has been doing, because I think there's lots to learn and share here. So thanks to Chevalley and François and Olivier for organizing this. I'm located in Southern Oregon, and I've been doing spectroscopy for a while, and I'll go over my equipment and also my approach to automation. But one of the things that occurred to me as I thought about automation is you really need to automate the entire process. It isn't enough to put it on the star on the slit, although that's often the hardest part, but you need to be able to control mount pointing, your camera, image acquisition, and the spectroscope itself. So ideally, you want a system that lets you manage the entire process. Also, I wanted my system to be as simple as possible. I worked with some commercial software that used binary encoded control files and so on. I wanted to have text format control files that I could either generate simply or just copy and modify. I also wanted to use as much free and open source software as possible and make it sort of platform agnostic. And also, the system should be easy to modify. Now, GetSpec, as you'll find out, is really aimed for my system. It works really great for me. But as François said, there's no simple single approach that works for everybody. It depends on your equipment and what you're trying to do, but you'll see what works for me. So what do I have for my equipment? I have a PlaneWave L350 mount, which is key to the entire process because it can accurately and repeatably put the target star into the guide field of view every time. And by the way, my guide field of view is very small. I also am using the PWI4 software, And PlaneWave has published a Python interface that will talk to that software. So I'm able to control the mount through Python. I have a PlaneWave CDK 14-inch scope, and I'm using PWI 3 software just for fan control. Luckily, that scope is really fairly insensitive to temperature change, so I don't have to do much focusing. I have the motorized UVEX with both the guide and Cal modules. And again, the UVEX has embedded control software available that you can talk to with Python. My science camera is a ZWO ASI 183, and I'm using Maxim DL to control it. And that's the one thing we'll talk about future possibilities there because that is Windows specific. My guide camera is an ASI 174, and I'm using PhD2 software. PhD2 also comes with a published API, and a nice fellow named Andy Galasso actually published on GitHub a Python interface into the PhD2 API, so you're able to talk to that with Python. And I also am using a DLI power control, and this lets you control individual outlets using a web interface, but it also has a Python API. So you're getting the common theme here. Python is the control language. And here's my observatory. Luckily, I have pretty good visibility, pretty good skies, although it gets a little wet in the winter. And I wanted to point out this is obviously the UVEX here, but this is that DLI power controller, and it just has a web interface that lets you turn individual sockets on and off, but also has a Python API. So what is this GetSpec? Well, it's software that I wrote, and it's written in Python 3, and it controls the mount, the power controller, the UVEX, Maxim, and PhD2. It's currently about 1,100 lines of Python in the main control program, and then I'm also have access to these libraries that these companies have put out. Currently, it requires Windows because of Maxim, and I'm actually talking to Maxim through the COM object using Python. But as we'll talk about, there's some future developments that are going to remove that restriction. It's really simple to use. I'll show you the interface, but you basically select a control file and say run and go to bed, and that's it. But it requires a very specific equipment configuration, my equipment. Here's what the interface looks like. So you really just prepare this text file. I'll show you a bit of what that looks like. Select it, click run, and away it goes. And these boxes here give some status as it goes, and it creates and saves a log file too. So when you get up in the morning, you can see what happened. How does it work? It's actually very simple. Initially just connects to the mount, the L350, homes the mount, slews to the target. This is all easily done using Python, AstroPy, and the library that PlaneWave publishes. The L350 has to have an accurate sky or pointing model, and that's the whole secret to it. With the model that I've built for my L350, and maybe I'm just lucky, it always puts the star near the slit. And as François said, you never get the star on the slit, but it puts it close, and that's key to the way I do it. I know the PhD2 slit coordinates. I've determined that ahead of time. All I do is I set a region of interest. This is all, again, using the API into PhD. I set a region of interest that includes the target star. I start PhD2 guiding through the API. I set the lock position to the slit center, and PhD2 will drive the star onto the slit. So it's actually very simple, but it requires that this region of interest has to contain the target star. So you might ask, how do you get that region of interest? A lot of the work I do involves multiple visits to the same star night after night. So normally if I'm starting a new star, I'll just take a quick image, make sure the star is in the position I expect, and record a region of interest, put it into the text file, and away I go. So here's a little bit of what the control file looks like. And again, just a text file. So you connect to the mount, home it, define the slit coordinates. So these are known ahead of time. I'm using a profile in PhD2, which sets all the guiding parameters. Connect to PhD2, set the region of interest. So it's a box. Set science camera binnings. I'm using a subframe on the science camera. I wait for things to connect, wait for it to cool. Here's my reference star. I set a target name, set the UVEX to calibration mode. And again, you can do all this through the Python API. Take some cal images, set the UVEX to the sky source, which is the object, wait a little bit, set a PhD2 exposure time, tell PhD2 to start guiding. It will use the ROI to find the star and guide on it, set the lock position, and it'll just drive that star right onto the slit and start imaging. So that's all there is to it. But again, requires that the star be in a repeatable position. And for those who haven't used PhD2 to do this, once you get the star into the guide box and you've defined your slit ahead of time and do the set lock, it will reliably drive the star and use the guiding parameters that you set up. Again, I don't want to reinvent guiding. I don't want to reinvent all the guiding algorithms. PhD2 does a very nice job of that. And the API exposes all of the capabilities of PhD2 to Python. What about limitations? Well, yeah, there are limitations. The main one is you need a mount that'll put the target into a repeatable position. And again, either luckily or because of the hard work of PlaneWave, my L350 does. And with a good pointing model, that always works for me. Currently, the way I've done it, I'm guiding on this target star in the slit. And there's some ways you can think about guiding on stars outside the slit. And I think Pete Velez, especially at the end, will talk a little bit about some of the work he's done in that area. And that's something I'd like to implement. It does work best for repeated visits to the same target because I have an ROI that I know will work. So I don't have to think about that. But again, given these limitations, this works really well for me. I actually work on a Mac. I start up with remote desktop access, a little headless PC in the observatory, start up, get spec, go to bed, and get up in the morning, and it's finished. Works really well. Also, one of the reasons I did this was I want to learn about what some of the limitations are to robotic spectroscopy, and for me, writing my own program was a good way to do that. What's coming up? Well, I'd like to get rid of the Windows requirement. I'd like to be able to run this entirely on a Mac or a Linux box. And one of the things I've started to experiment with is Alpaca. And Alpaca is a Python interface to the Alpaca library. And for those of you who aren't familiar, Alpaca is largely an effort of Bob Denny, I think, but it lets you access ASCOM drivers for things like cameras across the network, regardless of the system they're sitting on, as long as there's an Alpaca driver. And fortunately, a lot of systems have Alpaca. And I think there's Alpaca Pi right now that is a complete implementation on a Raspberry Pi that lets you access it. So it takes Windows ASCOM out of the equation. And I've actually written a get photo or photometry application using Alpaca, and it seems to work really well. I also want to be able to guide on an offset star, and that wouldn't be too difficult. I thought about adding plate solving as a backup method, but I tell you, I was saying this to François earlier, with my small field of view, it's just not reliable. Sometimes I can plate solve, most of the time I can't. Maybe there'll be some hardware developments in the future that will help with this. The other thing is I'd like to be able to verify that I do have the right target star because occasionally there'll be some confusion. And one thing I've thought of is if I added a filter wheel to the guide camera and centered on a star, I could get an estimate of B minus V. And that might tell me by looking up in Simbad whether I'm looking at the right star or not, or at least tell me if I'm looking at the wrong star. Anyways, a couple of ideas I've been thinking about. But that's it. Basically works well for me. It's very specific to my application, but it's been a lot of fun developing it. And also, I'm starting to realize things that I could do better in the future. And that's one of the great things about a seminar like this, seeing what other people are doing. So that's it for me. Thank you very much.
Thank you, Sean. Thank you very much. We have a question from Gary asking regarding your pointing model. We have a question in the chat asking for your pointing model. How many stars did you put in your pointing model?
Yeah, I think I've got my approach was I defined a very dense model, like 200 or 300 stars, and let it run automatically. A lot of them wouldn't plate solve, but of the ones that did solve, I covered the sky in maybe 120 stars, so fairly dense. But my approach was just define a dense grid and let it find whatever worked. I use the PlaneWave software.
Okay. So now, I don't think
I will say, Francois, that in all of this, and I think you're finding this too, your mount performance is really going to be the key to making this work.
Yes, absolutely. Well, on my side, I know that I do have, well, the big mount I have is 10 microns. And I know I can also make automatically a pointing model using K-stars. And on my side, I use something between 30 and 40 stars for the model. And I feel that, like you described, the star is in the gut image in any case, and close to the center. Okay, so thank you very much, Thierry. I've seen that you are around.
Yes, I'm here.
Hello, Thierry. You have
Hello.
the mic.
So I live close to Paris. This is the observatory in a suburban urban city called Chelles. So Chelles, yeah, this is the map. I'm 15 kilometers away from Paris. There is a UIU official code name. Urban environment. The thing is not so bad. 2 to 3 arc seconds in long exposure. And the observatory is dedicated to spectroscopy. I tried some imagery, but the sky is very too bad for imagery. The limiting magnitude with naked eyes is like 3.5. So when I tried, in fact, even with a very small telescope in the countryside, you do better. This is the setup. I have a 3-meter dome from Scope Dome, and it's a recheck Retier 36 centimeter at f8. The mount, it's a German mount, classical German mount. With a relative encoder, no absolute thing. So robust mount, but simple mount. The spectrograph, I have many, but the most I use is eShell for high resolution. And the LISA is a low resolution from Shellyak also. The setup is fully automated with mostly Prism software from Cyril Cavador. And I use several Python scripts. The idea is I feed the system with a big list of targets, and there is a weather station, and when everything is okay on the weather, yeah, the system start, open the dome, etc., etc. At the end, I implement a database to store everything automatically with like MySQL, PHP interface to see what is, but yeah. And there is also a reduction pipeline. I use easy software and yeah, an automate software to click on the Easy box. For the guiding, that's most the focus today on this guiding and pointing. There is two optics: the field guider, so the guiding system. The focal length is almost 2 meters. I use a focal reducer. And with my camera, in theory, I have 15 arc minutes per 10 arc minutes. But in reality, due to optical aberration, the field is smaller. And I have a very small number of stars. I will show you. Due to my sky is not dark at all, huh? So I have a lot of light pollution. And to help me, I use also a finder. It's a small guide telescope, huh? With a camera. On this finder, I have a pretty much a bigger field, around 1 degree of field. Huh? So with the finder, the plate solving works very well. So that's my guiding field, an sample. That's the eShell bonnet. In the center, there is if you see my mouse pointing, there is a small dot, dark dot. It's the entrance of the fiber, optical fiber. So on this spectrograph, yeah, it's not a slit, it's a fiber. So it's small, huh? And this is a sample of my pointing. You see, the star is here. It's approximately at 4 arc minutes of the good position. I don't implement a pointing model, so it's really like this, with no correction, nothing. On the polar limit, it's perhaps a little older, because I think I did it 5 or 7 years ago. I'm pretty sure I need to redo it now. And yes, the idea is I use plate solving. So when I do the plate solving, and after I do an offset move, and yeah, I obtain the right imaging. So the target is on the slit, on the fiber entrance. That's another example. On this case, the pointing accuracy was better, but not enough. Huh? I use this process to do a survey. The survey ID is looking for newbie star. So I select 1,300 stars in Simbad. So that's, yeah, all the stars I observe in red, the red dot in galactic coordinates. So the majority of the stars are in the Milky Way, in fact. And I do some statistics. And finally, the astrometry works in 96%. So I have only 4% of the star for the astronomy failed for 4% of the star only. So that's not so bad. My idea is I have different kind of targets. The first kind of target is, my 4% is in some cases I have no astrometry possible. And this for now, in my point of view, this kind of star I cannot observe in with automation. So an idea is to improve my field my guiding field, optical quality of the guiding field to reduce this statistic. But yeah, for now, it's like is this, like is it. It works most of the time. And sometime when the number two, it's the astrometry works and the target is bright enough. For example, for me, it's like brighter than magnitude 13. And in this case, I can use the guider to directly guide on the target in the slit or in the fiber. So I use the guiding software of Princeton directly. On the third kind of target, it's what I call the dark target. I'm very interested in the planetary nebulae, but yeah, I cannot guide on planetary nebulae. But what I do is find a guide star very close to the target, and in my script I define the coordinate. In fact, I define the coordinate of the target and the coordinate of the guiding star, and that's enough to determine an offset guiding. So I determine in my field where to put the guiding star to have the target in the correct position, and that works good. But of course, you need to know exactly field orientation, scale, everything. But you do that with astronomy, plate solving. That's the global algorithm of the observatory. First part is start the observatory, do a first finder astrometry to recalibrate the moons, because there is no absolute encoder. And when I start with a target, here, Schindler gets the next target. I look if I have to switch the side of the pier, if I have to switch to another, to the east or west, depending on the position target. I do an astrometry on the finder to recalibrate the mount or not. Then I point the scope to the target, do a field astronomy, astrometry on the field. If it's okay, I start the guiding and take some picture of the field also. Start the guiding and start the spectrum. Okay. And the point is if the astronomy failed the first time, I retry one time. In fact, I try again to use the finder and retry the thing. And after 2 times, I let it go. In fact, I switch to the next target. What's next? For me, my main limitation is the guiding field. So I plan to improve the guiding optics. One way for me is to use there is in France UVX4 project. It's an open source UVX in 3D printing with people from Nice, the nice people they call it. And they improve a little the guiding optics. So I will try to reuse this. And another approach is to use small objective on the shelf, because I know if I put 2 small objective, one objective to focus, to put everything to the infinite, and another one infinite to the focal plane, that can give me a very nice field of view. And so that's my first idea. And also I need to finish my hardware indie migration, because when I start this 10 years ago, I do everything in Prism, but I want to migrate everything to the Linux, the Python thing, migrate everything. And yeah, I have some works to do on this subject. And yeah, I have some plan also to use the CCDCL software because I already tried it on not with automation but manually, and it looked great for me. And I have some idea also to put the star in the slit, but perhaps not using the astrometry. I think astrometry is good, but it looked like overkill for me because the moons are not so bad, and we know we are very close. Normally, the target is very close. So I find I can use cross correlation imaging on the image to put the target in the slit. So I will try to use this kind of algorithm. And perhaps it can work with only a few stars. Yeah, that's it for me.
Thank you so much, Thierry. I see we have another question in the chat, but maybe we'll keep it for the end of the discussion. It was regarding the if the star is not oscillating in the slit, and so we'll keep the question for the end of the discussion. Okay. And so the next speaker, if you are okay, is Patrick Fricker.
Hi, everybody. First of all, I would like to thank Chevalley and Olivier for giving me the opportunity to share my experience. I'm living in Switzerland, and I'm having setup in south of Spain at EI with a pretty good sky, over 260 clear nights per year, and a seeing below 2 arcseconds. Regarding the setup, I have a mount with 3 scopes. With a high resolution scope is a C11 Celestron C11 at f10 with a Laris with a 23 micron slit, and a low resolution in RC10 with an UX. Regarding the software, the whole system is fully automated. I wrote Python scripts to take care of the observatory, to take care of the sequencer as well. Out of a database of 1,000 stars, the system, the Python scripts select automatically the relevant targets depending on the sky, on the time, on the priority, etc. The acquisition, I decided to use CCDCL, a very, very nice piece of software. We will hear more later, and as well with Python scripts to talk to CCDCL. The whole system is not attended, which means I press a go button in the evening and the whole system works automatic throughout the night. The processing, I decided to work with SpecInti, with Visual Spec, and with Python scripts for the analysis of my results. And what I do with it, I publish my results to BESS, ARAS, AAVSO, and other online databases. My high resolution setup, I would like to talk a bit about it today. Basically, I would like to talk about the issues I have with it. Most of the target I'm looking for are magnitude 7 and less. The equipment, as I mentioned before, the model is incomplete. I've only around 50 stars, which is not very precise. The science camera is an ASI 533, and the guiding camera is ASI 174. I choose the slit of 23 micron for the maximum resolution. But The problem is that my field of view is very, very small. I've only 10 by 16 arc minutes. It's the only field I have to find my target and to center my target. I did a choice is using my guiding camera to position my scope. And this has a lot of problems, makes a lot of problems. My strategy, the first thing I do, I point my scope. I try with ASTAP and astrometry.net to do a plate solving. If it doesn't work, I wrote my own scripts to try to know if my target is in the field of view, but the system is not able to do an astrometry, or if the target is outside of the field of view of my guiding camera. And if I'm able to bring the target into the field of view, then CCDCL takes care for the auto-guiding itself. There are three situations. The first one is with ASTAP and astrometry. If I'm looking for targets in the Milky Way, like BE stars, plate solving succeeds over 97% of the time. Even with such a small field of view, it's not an issue. Which means most of the time, most of my targets, the system works perfect. But sometimes it looks like this. Alpha CRB, just a black screen, a black image, and I have no idea, I have no clue where I am. I'm not able to do a plate solving. I don't have a finder camera. I only have this image. And what I decided to do, I decided to create a Python script to move the mount 10 arc minutes by 10 arc minutes around this place to hope to find a place like the yellow square on the screen to be able to do a plate solving to go back to my target. It works well, but it's very time consuming. Sometimes it takes me up to 10 minutes just to make sure that I have a star in the middle. Maybe not a target, but a star. Which is the second case. The second case is I have a star in the field, but I'm not sure if it's the right one. I'm not able to do plate solving, as I said, but I have a star in the field. And what I do, I created a script as well to move with the offset, because the plate scale is known. I calculate the centroid with Python, and I center the target in the middle of the slit without being sure if it is the right target. And what I do, I look on SimBand with Python for the list of stars around within more or less 10 arc minutes and look for the brightest star. And then I have the coordinate. With the coordinates with my plate scale, I should know the X and Y position. And if I have a match, then I'm sure it's the right target. But it's time consuming as well, because if it is not, I have to start again. Which means the only valuable solution to make sure the things go right is to have a successful plate solving. What's next? My goal is to add a separate pointing scope, like a small finder scope, to create a model with this finder scope to make sure that any targets I'm pointing at, I will have the star within the field of view. With this, I will refine the mount pointing model. And as I said, I will create a model to compensate the flexures. And regarding the guiding accuracy, I will go and try a multi-star off-slit guiding. At the moment, I choose the solution of CCDCL with a single star, which it takes the brightest star in the field and center it on the slit, but I will try to do a multi-star off-slit guiding. That's my experience with this. Thank you.
Thank you very much. Thank you very much, Patrick. I'm just checking the chat. No, we have no questions so far. Okay, thank you very much. Thank you very much, Patrick. And we can continue with the other Patrick. So this is Patrick Chevalley, CCDCL.
Hello. I want to present you today the CCDCL software to use for spectroscopy specifically. CCDCL itself is not a new software. I started it about 12 years ago when I want a software for Linux. Now it works also on Windows and Mac and can use multi-protocol access to different drivers in the Alpaca or ASCOM. Recently, about 3 years ago, I was asked to add spectroscopy function to CCDCL by Pierre Dubreuil from Nice team. We try to automate the UVEX4 as much as possible. Now, there is specific spectroscopy function in this spectroscopy tab is here in the internal guider, and this is why we will look in detail today. Just to present a general presentation of the software, you have the main camera with the spectra here the finder camera with the offset for the centering on the slit, and here the guide camera with the target on the slit, invisible on the slit here, and the guide of star offset here, and the internal guider will take account for all of this. Though the first step when you want to automate pointing, as Patrick just said, the more easy is to use a finder camera. A finder is a small scope parallel to the main. It is not perfectly aligned with the slit, so you cannot do astrometry at the center of the finder. You do astrometry with an offset. There is a specific tools in the software to calibrate the position. So you put a bright star in the spectroscope, start guiding on the slit at the position you want, click the calibration measurement. It takes a picture of the guide camera, plate solve, and locate the position of the star actually in the slit. So this is for future pointing. All the target will be put here. So this works well if it is good good rigidity, no flexure with the main instrument. This is the main requirement. The main problem is when you change the side of pier. Side of pier, sometimes you have a small offset here. This is an indication you must improve the fixation of this and have a very rigid adjustment of the guide scope. After that, here in this spectroscopy option for the guider, you have a list here of 5 methods you can select depending on the target, depending on your equipment. The most simple is a single star, as we do with PHT2, and it will take a star near the guide position on the slit. Here vertically I draw the slit. The green cross is where we want to put the star for guiding. And it's first search in the guide box area. The guide box size you configure here. Here the star is not in this position because the finder is not well aligned and it is a bit out. So we have a maximum search box bigger than the search area where it search for the star. Though this time it find the star, it put the guide box in and draw the star to the slit. This is an improvement. It is necessary to be careful to not put this too large, just for the pointing error, to not get another bright star in the vicinity. Second option is guiding white offset. This is a very nice method where you know offset position between the target and the guide star. We will compute this offset between the two stars, apply this same offset from the position we want the target and the position we need to put the guide star for guiding. So it is necessary to indicate to the program this offset. The most simple is you click this button, click on the image. So you push this button, you click on the target, you click on the guide star, and everything starts. This is for manual use. For automated use, you have a script command to give the offset in pixel. If you have a script method to make this calculation with your method, you can compute the offset in pixel and call this script function. You can also use a standard script provided by CCDCL, where you give in parameter the coordinate of the guide star. So here you have our target. This is the coordinate of the target, and here the coordinate of the guide star. This requires a single astrometry of the guide system to calibrate, so it can transform the offset, the coordinate offset in pixel offset. For that, you need to point your telescope in the Milky Way, dense field, have an open cluster, take a long exposure, plate solve, and this is calibrated. Now you can use this method everywhere in the sky. The three last methods require guider astrometry. So this is not for every setup. Short focal is good. Large guide sensor may be a solution. It needs also large optic, eventually on the guide system, for a good view of the guide field, enough star for plate solving. If you can do plate solving, you can improve the single star method by an astrometry. This astrometry just makes sure you select the right star. In this case, we have the pointing of the telescope was not very good, and if we select the first method, it probably get this star or maybe this to the slit. This is not the one we want to measure. Wide astrometry, we are sure to select the right star. It put the guide box on this one and draw it to the slit for the observation. So this is a very reliable way to get the target on the slit, but require astrometry. Just an additional option here, you have a different exposure time for the astrometry and generally a longer exposure time than for guiding. The next method is about the same for the centering, but when the star arrives on the slit, it's stable guiding here. The program automatically switches to multi-star guiding for to prevent oscillation of the star on the two sides of the slit. So with this method, we are very stable guiding, and the arrival of the star on the slit is detected by two methods. The first is if the target is bright enough. This is when the guiding is stable here, though you switch to the other method. And another way to signal it is on the slit is we lose the star signal. If the star is relatively faint, it is possible we totally lose it when it is on the slit. So a star loss is considered at the arrival at the star at the good position. The last method is totally multi-star gather astrometry. This method is very powerful because it not require the target is visible on the guide image. It is enough with enough star to make an astrometry. This compute the position of the target, even not visible. We have the offset. This offset is applied to all the stars of the field, and they're moved. Every star is moved, so our target go on the slit for the observation. There is a few requirements for this to work fine at the moment. This requires high quality tracking. There is no periodic error on the mount. This work fine actually only white mount, white guiding encoder to ensure we have a very well tracking what you're guiding. This is because we have a time delay between the picture we take for the astrometry and the moment we have the solution of the astrometry and we take the first guide exposure to look at the star. If the mount is moved during this time, we are not unsure the star really go on the slit. It can go a bit out. And with this method, we have no feedback on the slit. So it can be a bit outside and all the observations are lost because of that. So this method is a good one, but it needs improvement and actually work only with very good mount. For automation, we sometimes have also to offset the guide position during the night and to not lose the position, the main position we have set on the beginning of the night. Maybe we want to make an observation on the wide side of the slit, and we define an offset so we can quickly switch between the two. What you modifying this setup is the main setup. This is also used with the motorized slit of the UVEX4. UVEX4 have 4 slits you can change during the night, and sure they are not the position of every slit when the slit support rotate is not guaranteed you arrive at 1 micron precision here. One slit can be here and one a bit here, so you set the offset here. All of this can be used with the internal scheduler. Here is a list of BE star, many hundreds of BE star. For the automation, we set up when we want to observe them. Here, the IMC is meridian crossing. So we start observing 3 hours before meridian stop, 3 hours after. Only during this, we observe only the target when there are good location. You can change that to one side of the meridian if you not want to make meridian flip. You have the magnitude of the target here. And with this magnitude, the script here to initialize the guide system automatically update the guide system exposure time for the magnitude of the star, because we use single star, though we guide on this star of this magnitude, and sure we not take the same exposure time for a 7 or for 2 magnitude star. It also, here is the step, the template of the step is here. We start with calibration light, calibration frame, then take the spectra. The spectra use a star auto exposure, with the magnitude here to determine the exposure time. It takes 5 images. Stop the tracking, so we not have the star image with the next calibration. Take next calibration and start the processing with SpecINT software for this observation. So we have the spectra that arrive on the fly, processed on the fly on the system. So this is a target I like to use for testing the guiding, because this is a difficult target to, when you guide on the smallest star, you know, Albireo star, the BA star is the blue star is the fainter one. So here it was selected using astrometry. We're sure we not guide on the yellow star here, but get brighter. It is important to use a small guide area, so it not switch to the brightest star on the fly. The red line here is mark the movement from the previous position to the expected position. We see here my mount is not very good. The star is a bit off of the expected position, but it is in the yellow box, so the program drive it to the slit. What your problem? When on the slit, it is very critical to not switch to the bright star here and to get. Sure, this is, I use this for testing the software, for testing the guiding for a real observation. The good strategy is to use the guiding white offset, use a shorter exposure time to guide on the brightest star, and put guide here with the target here on the star wide offset. Here an example of guiding white offset. This is the supernova last summer, and here we have the galaxy. The supernova position is here. It is totally invisible in the slit here. And the guide star position was given by the automated script in the sequence. Everything was computed by the software, and the centering for this observation was totally automatic. I look at it to make some screenshot, but I not touch anything during this observation. You see the guiding is good. This is quite good guiding for my mount. This is an EQ5, and the telescope is a small 6-inch Newton. So this make a nice spectra for this small equipment. Here the team of NIS, we work a lot on the software to make all this work. We already discussed future development. Next is using the rotator to keep the slit vertically relative to the horizon to avoid atmospheric refraction effect on the slit. I want to add support for parallel instrument, for example, for simultaneous photometry of the field. And you have always a lot of idea, sure, with your different equipment. And I have always request for new function, and we always look if it's possible, and we try to implement it. Okay, thank you.
Thank you very much, Patrick. Are there any questions? No, no question. In fact, I do have one question for you, Patrick. When you compare the 5 methods that you offer, well, I do consider that the fifth one is probably the best one, with the condition that you can plate solve in the guiding image, of course. You say that you have to have a good tracking because you have to stop the guiding while you are taking a long exposure to do astrometry, to do plate
Yes,
solving.
you cannot guide when the long exposure for
Absolutely.
astrometry is running.
Absolutely. But do you consider, I don't know, how long is the plate
So
solving
at the
operation?
moment, I need to improve that. I think it's possible to improve because we have the location of the different star on the field,
Yeah.
and at the moment it used the position found on the astrometry image.
Yes.
I think it's probably possible to start the guiding, locate the star on the guide image near the position of the astrometry and reset the offset at this time. At this time, it not do that, and this is the limitation. But I think it's possible to improve that because if you have I say the moon move by 5 pixels during this time. This is not this is about what my small moon do. It is 5 pixels out, but at 5 pixels, if you keep the position, this is wrong. You will not go on the slit, but this is enough to identify again each star. And I think it's just to add a function for that to re-identify the star on the first guide image and quickly reset the position, recompute the offset position. But I have to do that and test.
My question, in fact, is if you stop guiding for a few seconds and start again, you can just do the guiding auto acquisition, restart the guiding, and after do the plate solving. And you know.
Yeah, no, but because we need a long exposure for plate solving, we cannot plate solve with guide exposure time of 2-3 seconds. It's not enough for plate solving. I use at least 10 seconds for plate solving.
Okay, and
10 second exposure. And this 10 seconds plus 5 seconds for astrometry. Even if local astrometry.net nice calibration, it takes about 5 seconds. But this is enough to have an offset.
Okay, but my point was just you can restart the guiding before plate solving.
Very good mount. Probably with the plane wave, it's not a problem. With a skywatcher, it's a problem.
Yeah, my point was just to say that you can restart the guiding just after taking the guiding image, and then you plate solve after to not wait until the plate solving to restart the guiding.
Yes,
Do this.
You say start guiding and plate solve in parallel.
Yes, absolutely, yes.
Yeah.
Well, okay. Thank you very much. Thank you very much. Now we'll switch to Olivier for the spot. Thank you, Olivier.
So, yes, I will present, in fact, in place of Stéphane Charbonnel. So, I will present the method developed by Stéphane Charbonnel for our two-spot spectroscopic robotic team in Chile. So, this is not my my software. This is the script did by Stéphane. So for robotization, for soldering a target into a slit or a hole, because we have a E-shell spectrograph, we work with optical fiber. So it's for us, it's a hole, it's not a slit, but it's the same problem. even if it's a slit or a hole. And this script is made with Prism software. This is an old software, but it worked very well. And what we did, so there are some prerequisites to have the best result as possible, because for example, the mount. If you have a pointing model, if the pointing model is possible with your mount, it's better because you take less time to plate solve the final position of the star into the slit or the hole. But this method can work with if you don't have any plate solving, or no, it could work with if you don't have any pointing model in your mount. But it takes more time to get the result. The second thing, it's that the field of view of your guider imaging must be large enough for astrometric prediction for the instrument, depending of course of the focal length. If you have a large focal length, you have not many stars, so it's difficult for plate solving to have a good result. So you can increase the chance to have a good astrometric prediction with using a sensor, a large sensor. And we use I174 camera because this sensor it's quite bigger, so it take a good result with this kind of sensor. And of course we use Prism software. There's a special feature in this software, the astrometric center, and it's very useful in our case because we can define anywhere in the image, in fact, the real center of the pointing when we point a target. And in this case, you have to use Benning 1.1 in your image. So here is an example. Don't worry about the quality of the image. It's not we have, but it's just a screen copy, quick screen copy of we get in Chile. So you have the target. This is in fact the first go-to. So the software automatically decide which kind of target he can do during the night. So, for example, he points first time the target, and here is it the first pointing. And of course, we have the pointing model that, in fact, the target it's close to the Faber hole. The Faber hole is just the black dot you see here. It's a very small black dot here on my mouse pointing here. So you see that the target is not is close to the black hole, but it's not on the optical fiber. So you need to do astrometry on this picture. And first you have to define the real position of the fiber hole or the slit. How we can do that? We just put on the flat lamp on, so we illuminate the slit or the fiber hole, and we take an image. We put the image in negative mode, and we have this kind of image. And we saw here that there is a small gray or white dot here. This is the real center of the optical fiber entrance. Or if you have a slit, we have a rectangle, a white rectangle. So we can define exactly the position of the slit or the coordinate of the X coordinate and Y coordinate of the hole. So, in fact, when we do have this, we are able to, in fact, to another go-to to put to slew the target into the real position of the hole in the image. So here you can see that the target is on the fiber hole. So in this case, it's good, and we can start auto-guiding on the target, or we can choose a star close to the target, and we can auto-guiding, for example, on this star here, it's close to the target. But we can also auto-guiding on the target. Then, in fact, there are, we have the choice to centering the object on the slit. In fact, after 2 measurements, the object is already very close to the reference position, hole or slit. And the auto-guiding is based on restriction X and Y at the exact reference position, intensively and within a small window where the object is located, in order to guide into the hole. So that's what Patrick showed in the previous presentation. If we draw, in fact, the software draw a box around the guide star to be sure to guide on this star and not on other star, maybe brighter than the guided star, to prevent any issue in the auto-guiding. And then how the software decide which kind of target, which kind of star we need to for auto-guiding. So in fact, the goal is to determine a guide star outside of the target star in order to avoid in fact, you know, I don't know really the word in English, but yo-yoing say, in fact, that if you guide on the target itself, you have some shift movement of the target into the slit or into the hole, that sometimes it's up, sometimes it's down, but it's never exactly on the hole, on in the fiber. So in this case, we need to find another star in the field of view of the auto-guiding field of view, and we have to, the software have to choose, in fact, which kind of star he can find in the field to auto-guiding on. So with our instrumentation, we have choose, in fact, 3-second exposure, not too many exposure, because our goal is to take many target during night. So we expect to take minimal time to find the right star to auto-guiding. He decided to search in 2 rectangles, of course outside of the slit and outside of the hole, and in fact he find the brightest star present in one of the 2 rectangles. And for example, in this case, he will guide on this star here. That's the most bright star of all the field of view. And then he finds this, of course, the target is in the hole or in the slit, and then the software decides to auto-guide on this star. Then, in fact, after of that, that's the final image of my presentation. At the end of the night, in fact, all our setup have automatically take more than 10 targets during the night, then process all the spectrum automatically, and then we have a review of each target that the software give us, in fact, the result in a graph like this one. and we have the result for each star automatically. There are no human intervention in the result. So thank you for your attention.
Thank you very much, Olivier. Wonderful again. Well, even if we know for some time all what you're doing at TwoSpot, and it's really great. Thank you. I see again there are a few questions, but I think that we've also already the answers in the chat, especially regarding the documentation and for the CCDCL and its ability to track to control in Alta's mount. So I'll let you check in the chat. The next speaker and last for today is Peter Velez. If you're okay, Peter, this is your turn.
Okay, I'll just share my screen. Okay, hopefully that's nice and clear. Well, good afternoon or good morning, everyone. The sun's finally up here this morning in Sydney, which is great. I have been running my spectroscope up at Siding Springs Observatory for the last few years and have been working methodically through trying to get it automated. I think after having heard all these presentations in French earlier this week and then heard them again today, I think that my presentation will be more about an historical background on what I've done and how I've got here rather than what I'm going to do going forward, because I think there are quite a few issues that have been discussed which are going to give me reason to reconsider how I do things. But let me just take you through a few points. In a high level, I'm going to give you some background on my system and my objectives. I'm going to discuss 3 different methodologies that I use. Each provides ways of addressing different issues. There's the plate solve model basis, which is essentially the astrometry-based system that people have been discussing already today. The guider-assisted slew methodology, and then what I would consider to be the bleeding edge, which is the more challenging aspects of what I'm trying to achieve. I'm going to focus on approach rather than specific code to talk about how the logic that underpins how all of this works. I think a lot of this has already been discussed, so I'll try and zip through it reasonably quickly. I think the one thing I do want to emphasize is that as has been discussed before, there is no one single approach that will address all issues. We need to have a multiple of different methods to be able to achieve our objective, which is getting the target onto the slit. I will say this to you all, that I'm happy to share anything that I've prepared, but reflecting the fact that I'm an ex-corporate lawyer, I have to show you a disclaimer. You can see it up on the screen. You're welcome to use it, but it's at your own risk. Here's the observatory. I'm in the Eye Telescope facility on the mountain at Siding Springs. It's a rather large shed with many very big telescopes in here. Here's my modest telescope. It's a 12.5-inch CDK from PlaneWave. I'm using the UVEX, usually with a 600 lines per millimeter grating, with the motor unit, which has been a game changer for me. I have the Alpi guider unit, and like others, I'm using the 174mm as a guide camera because it gives you it's a nice big sensor, gives you a good field of view, and it's cheap. The mount is a Paramount MX. It's about 10 years old, and it's showing its age. It does enough, but it could be better. And after having lusted after an L350 for a while, I've pulled the trigger on that recently. So hopefully that'll be arriving between now and Christmas. I have a rotator. You can see that built into the front of the system here. And I've got a piggyback refractor, so I can take photometry at the same time as I take spectra. What do? My focus is on low resolution spectroscopy, which means that I'm going to be looking at a lot of stars, looking at stars that are going to be fairly faint, which presents its own challenges. And most of what I do is looking at transients and doing rapid response to things that arrive. So keeping an eye on alerts that appear on CBAT or the Assassin website and responding to them quickly. This means that many of my targets will not appear in SIMBAD, and so I need to be able to respond to targets based on their RA and DEC. Software, I use a Windows machine. I use Voyager as my automation system. It controls everything else. There's a whole range of reasons why I decided on Voyager. I suspect that as a result of hearing Patrick's discussion earlier, I'll be shifting over to CCDL, CCDCL in the near future. I use Python scripts to automate some of the specific functions that I have. And I'm locked in at the moment to MaximDL for imaging. Key point that's been made earlier on, you can't use one method. So I'm going to tick through the three methods. So here's the first case scenario. The target I'm looking for is this one here. And what we're seeking to do is to put that onto the slit. As with most spectroscopes, whilst we have a nice long slit, we actually want to have it in a very specific place. So the optimum position I want to point the target is here. And that means that I need to point the telescope to this point here. A number of software programs have a way of doing this. Voyager calls it a precision slew. SkyX uses a closed loop slew, and a lot of other programs do the same thing. In simple terms, slew to where you think the target will be, take an image, determine, do a plate solve, determine the error, slew the telescope to address the error, and then take another image, repeat and repeat until you actually get it where you want it to be. As Francois mentioned earlier, the challenge we have is that this will not necessarily get us right onto the slit, but doing an iterative approach, it gets you as close to possible on it without having to do any fancy footwork. So I found the challenge was trying to identify what this position is here. So I wrote a Python script. This is the front end. It's based in Excel because I'm not particularly good on doing a web page. All of the fields in yellow are the ones to be completed. So the names of the target. The RA and DEC for the target, if it's a transient, I need to insert. The center coordinates for my system and the optimum slit position, some information about the observatory, and then this is the key, a reference to a plate solved image. So this is just an image I've taken with the same setup, which has been plate solved. In essence, what my system does is it works out the position angle and separation between these coordinates here, the center to the slit. It then determines using an AstroPy module, translate that into the real world coordinates, and it will generate this for me. Down the bottom are a couple of graphs, which I don't know about you, but I find it problematic to type in the number of a reference star accurately. So this lets me see whether my reference star is the right one, because I can see that the path of both across the sky are tracking easily. Gives me some information about observing conditions, but the key is these two lines. This tells me the RA and DEC I need to point at to put the star on the slit. And I use this for planning purposes. I just program my system to run to point at these coordinates. Because I do a peer flip, I'll go back. Because I do a peer flip, I have to have different coordinates west and east of the meridian. Pros and cons of this method: it's easy to implement. It works for a crowded field. It'll work even where I can't see the target on the slit. Downsides are that it requires plate solving. It does require good mount performance. And you have compounding errors, because if I plate solved an image, there may be 0.5 of an arc second error in the plate solve. If I then I can only get my mount to move within 1 arc second. Both of those could work against me, which means that I'm going to be off the slit or off my optimum position by 1.5 arc seconds. So something to keep an eye on. Second scenario, typical high resolution situation, bright star in the field, nothing else around. Obviously, I can't plate solve this. So what I do is using a guider-assisted slew, which is similar to what's been discussed earlier. Here's the approach. I've took a lot of comfort and started on this journey by talking to Sean Curry, and then David Sahuda also sent me some of his scripts for PhD 2. I'm implementing this in Maxim, so shout out to both of them for helping with this. Set the ROI, take the image, identify the centroid. Not as easy as you think, because sometimes you pick up hot pixels, etc. So you need to be careful with that. Start guiding on the brightest star. Then in Maxim, I set where I want to be positioning the star as the new guiding position. Maxim interprets that as a guiding error, and it will then try and drag the star from its old position to the new position, which is similar to what PhD 2 does, and I think CCD-SEAL does as well. I wait for the star to move, I take an image and check it, and then I repeat it if it's necessary. Restart the guiding and then start imaging. I've got a Python script that runs through all of these methods, all these steps. Advantages are it doesn't require plate solving. It doesn't require as much from your mount, because the mount's more responsive to guider instructions. It's suited for a high resolution system as well as for a low one, because you're looking only at bright stars, so it's pretty easy to find. You can adjust the field of view by simply changing your ROI to being a large or a small field, which is all pretty straightforward. It guides on the slit, but the downside is it guides on the slit, as we've discussed. And it does require an initially accurate slew. If you're not within the ROI, then you get nothing. And I think Patrick Fricker was talking about the challenge associated with this, how he needs to move his scope around to try and actually hunt for the star. And it's a bit fiddly in Maxim. One thing I found is using Maxim is that I'm using COM for communication, and that's becoming increasingly problematic with Windows 11. Here's the third scenario. This is one of the two NOVA that we had earlier in the year in the Southern Hemisphere. I call this the bleeding edge because I'm trying to use the UVEX for the purpose for which it was designed, which is UV work. The issue with UV work is you suffer from atmospheric refraction. If you are not perfectly aligned on the slit, then you are going to have distortion you're not going to pick up as much signal in the UV and the blue, and that then leads to an odd continuum. You can address this in part by observing at a high mass, but if you've got poor pointing errors, then that's going to present you with some challenges. So the usual solution is to align the slit with a parallactic angle. I think Patrick Chevalley mentioned this as well. And the other way I address this is try to guide on the slit, because at least then if I'm drifting and I'm drifting across the slit, at least if I'm drifting back and forward across the slit, I'm sampling the whole field. It's not perfect, but It's what I've been able to do to date. How do I do it? I determine the parallactic angle at the time of the observation, and this is critical because if you simply set up your system where you run and you start 3 hours before you cross the meridian and you run to 3 hours afterwards, the parallactic angle is going to be different at any given time, and it does depend upon when you actually start your observation. So you need to be able to do it in real time. So step one, determine the angle, then rotate the rotator to match the parallactic angle. Then I do a precision slew to put the target in the center of the field of view. I then calculate the offset RA and DEC, and bearing in mind that with my system, it will change if I've changed the rotator, because the position in the field will be slightly different. So I have to recalculate. I then recalibrate the guider because I've rotated the system. Then I do a precision slew to the offset RA and DEC. That gets the target onto the slit. Then I use a very small ROI around the slit position and apply method 2. That is to drag drag the target onto the optimum position on the slit. Then I start guiding on the slit and start imaging. It's a bit more involved. It's a combination of the first two methods, which mean that both methods need to be working, which is interesting. Pros and cons. It helps overcome atmospheric refraction, which is really important when we're dealing with the UV. And it leads to more accurate pointing because I'm using a combination of astrometry and the slewing, the guider slew method. We're guiding on the slit, which is good, but not so good. So there's some challenges with that. If we were able to guide off the slit, that would be better. It's not yet 100% reliable. I'm still tinkering with it, but I'm pretty close at this stage. What have I got left to do? Well, a whole range of different things. The first one I've been thinking of doing was variable guider exposures, so that rather than simply presetting the guider exposure, I'd like to be able to take an exposure, work out whether the guider, the star that I'm looking to guide on is saturated, if it is, to reduce it or to bump it up as required. The second is to refine the guiding off the slit, and I think the CCDCL methodology seems to have that covered already. I've got a method to do it, but it's a little bit complex as well. Final thoughts. Well, I'm finding this, I think Sean mentioned this as well, this has been really rewarding because it requires you to actually think through what you're trying to do with your observations. If you have something that works out of the box, then that's great. It's simple, but you're not actually thinking about how to improve your system. And I think this has been a really rewarding exercise for me. The other issue is domestic harmony. To be able to turn on your system, then go back to your glass of wine, dinner with your family, and go to bed. It is undervalued. It's really important. We need to focus on this more. Thanks very much.
Thank you very much, Peter. Wonderful, very interesting. I see the comments coming for everybody. When I see your presentation, you talked about the parallactic angle. And for me, this is and especially the fact that if you work in infrared or UV, you have to think to take that into account. This is typically the kind of parameters that makes that it really depends on what you are looking for, what kind of observation you are doing. So this is something very important for me in spectroscopy. You cannot have a universal solution to manage that, and that's a good point that you mentioned. Also, Peter, we did discuss recently, and we said, well, I think at the end of the day, we can say that we have two main tools, which is the plate solving and which is the auto guiding. And we have to play with these two tools. And knowing that the plate solving cannot work in any case, because when the field of view is too small, then we cannot, it doesn't work. So we don't have enough stars. And I know that, well, on our side at CHEIAC, we really work on that to try to improve the guiding solutions to increase the field of view and the optical quality to be able to plate solve in more and more cases, because this is really the key. Well, maybe I don't know if you have other comments or questions. I don't think so in the chat. I would just like to come back on the question. It was at the beginning. Regarding the oscillations of the pointing system. My small experience says that, in fact, for a long time, and I did say that, yes, we can use the guiding software, any guiding software, and we can guide on the slit, and it works. But, well, generally speaking, this is true, and I see that several of you are using this process because it is easy, because you just have to use the auto guiding software in a basic mode and so on. But really, what I've discovered with my script on measurement for the measurement of the slit position accuracy is that really, if you work with the slit, you have some local effect of the guiding, and well, this is really a pity. So I think we must, as much as possible, use a pointing, a guiding using a slit out of the slit. And now I also highly recommend to use the multi-star solution in any case where it is possible, because it is much more accurate, and we need this accuracy to work properly. Well, this was a general comment. So I think that even if you don't see any oscillation of the star in the slit, probably you better have to guide out of the slit to improve the throughput, in fact. Anyway, that's it on my side. Does anyone want to add something? Or last question? Last comment?
I've got one comment, if I may.
Sure.
Many things I've learned through this process, but one thing I've learned is how absolutely critical it is to have a good record-keeping system for your observations. So whatever system you use, a system that generates a comprehensive log is really helpful. And if you're also able to save images of your guided field as part of the process, it's critical, because there is nothing more frustrating than getting up in the morning to find your telescope has run for 6 hours and you've got garbage. It helps at least if you're then able to pull up an image of your guided field and to say, I didn't have a star in the slit, or that spectrum looks odd, I'm guiding on the wrong star, I've got the wrong target. So whatever system you use, one that has a log and also saves images is important. And I think this is the point that Patrick Chevalley was making earlier, which is the final of the guiding methods. The challenge I found was that I would start guiding, and then I would, because I'm using the guider also for plate solving, I would have to stop guiding to take an image, save that image to the file, then restart guiding. And in that interval, the star would have drifted off slightly off the slit. So this is the challenge that we face with using the system that we have.
Really agree with you there, Pete. And not only that, if you're going to return in a month to a target that you've forgotten all about, having a saved guider image showing you the star field is really handy.
Any other comment? Or maybe we'll stop here. One time, two time, three time. Okay, so thank you very much. Olivier, any final comment maybe?
No.
That's
All
perfect.
is good. So we have a nice workshop this evening for France, of course, not for Australian people or US people. But yes, I think there are many solutions to have a good accuracy of auto guiding on putting a star in the slit or a hole. So yes, there are many experience made all around the world about to make robotic spectroscopy. So it's great.
Thank you very much. Thank you for all the speakers. Thank you for all the attendees. And we keep the contact and we continue working like that. Bye-bye.